Hello, my name is Ed. Today's presentation will be about my FM2 auto report. So for today's agenda, we will be talking about the background, the objective, then the model setup, the problem parameters, the governing equation, and finally the results and discussion. So what are mechanical system? It is a physical component that can convert input motion into desired output motion. For the objective, it is to identify and specify input and output variables, construct the equation using the free body diagram. Um, once you have the equation, then come up with the transfer function as well as the state model, and finally plot the response using MATLAB. So for the model setup, for this mechanical system, the coordinate is x and theta. For the orientation, the translation would be the M1 mass. For x going up is positive, and for the gear, the rotational, it will be the rotational with theta rotating clockwise is positive. The reason why I use T as the torque as the system input is because it is the driving function, and mass one as the output. The output is because it is a response function, and we also assume that the system is initially at equilibrium. For the assumption, we assume that it is a rigid body, fixed wall and ground, ideal massless, linear spring damper, steady state equilibrium, gear not slipping and frictionless. The whole system would be frictionless system. The gear will obey linear torque and angular velocity. For the governing equation, it will be we'll be using the Newton's second law for translational motion. It will be sum of force equal ma with m as the mass of the body and ax as the acceleration. For the rotational, the gear, it will be sum of torque equal j alpha with j as the moment of inertia and alpha as the acceleration of the body. So as you can see here, this is my free body diagram. So I am assuming that Tm1, which is the torque related to the gear, and the mass M1. So this thing, I'm assuming that it is counterclockwise. It means that it will be negative. So since this thing is rotating counterclockwise, it means that mass M1 is going down. So if mass M1 is going down, then this Fg, which is the F of the which is the force from the gear, and the mass M1 is going down also. So if this mass M1 is going down, it means that the damper and the spring, it is pushing up mass M1. So I have the reaction forces as up. This Tm1 here, it is the torque. So torque is force time distance, but in this case, distance will be the radius. So that's why I have the F gear times R for the rotational motion. So rearranging the equation, I got this equation right here, and I call it number 1. And rearranging the equation for the translational motion, I got this one, I call it number 2. So applying the ideal gear 1-to-1 with x equal r theta, and then combining 1 and 2, I was able to get this equation right here. Using Laplace transform, assuming 0 initial condition, I was able to obtain this equation, which is j over r minus mrs squared. And then using the transfer function with x of s as the output and t of s as the input, I was able to obtain this equation, which is 1 over this j over r minus mrs squared. And then with the values plugged in, I was able to get 1 over 1.5s squared plus 18.325s plus 4.45. for state space representation, because initial condition qualify as state variables. Therefore, I choose the variable that specify the initial condition as state variable x1 and x2, as you can see here. So the state equation would becomes x1 dot equal x2, and x2 dot would equal this f equivalent times r over j over r minus mr. For the output variable, I am choosing one y1 equal x and y2 equal x dot. After rearranging the state space equation and the output equation, I was able to come up with this equation right here. This is my state space model. And then with the values plugged in, as you can see here, this right here would be my A, which is 0.1 and minus 2.97 minus 12.22. This would be my A matrix. The 0 and 0.67, this is my B matrix. The 1, 0, 0, 1 right here, this would be my C matrix, and the 0 here would be my D matrix. This slide, it is just about the matrix C of the model. Here you can see the A, B, C, and D. So I'm assuming that TFS, which is the input, is a step force. If it's a step force, then it would be 1 over S, and then plugging and then trend. If you move this TFS to the right hand side, you would get this equation right here. And then using MATLAB, I was able to come up with the residue and the poles. And then with the inverse of Laplace transform, it gives me this equation x sub t equal 0.0048 e minus 11.9 t minus 0.2295 e, 0.25 t plus 0.2247. So for this graph, I use MATLAB to plot it. As you can see here, that since this is a step response, so the torque is rapidly increasing up to 0.2, almost to 0.23. And then after 15 seconds, the system is at a constant. But the thing is, this system, it doesn't return to equilibrium. It will just keep on going infinitely. For the references, I use two reference. One is the website called Notes and Sketches. And then the other reference is the class textbook. Thank you for listening to my presentation. I hope you can give me some feedback and via email or through Zoom. Thank you.